So we are still talking about polynomials. We've been factoring them, finding all their zeros, and we're going to take that in this section and start graphing all these different polynomials. So we're not going to get all the way through the notes today, we're just going to do part of them. So a polynomial function, if you are looking, you will have something like
Seniors, please report to the gym for the work keys test and bring your charged Chromebook. Seniors to the gym with a charged Chromebook.
essentially all this means is that in a polynomial, you are adding together all different powers of x. I put this in decreasing order, so the power of x gets smaller in each term. That's kind of the standard form, but it doesn't have to be. So the terms could be in any order there. Your degree is always the highest exponent, not necessarily the first, only if it's in decreasing order. But in the scenario I wrote up here, my highest power would be n. The coefficients are all of those a values. So those numbers being multiplied with the x's. What's a constant?
Something about x.
So in my scenario, that would be the a sub 0. Just a term by itself. What is the leading coefficient? The way ours is written, it's that first one. Technically, it doesn't have to be. It's just the coefficient of the term with the highest degree. So a lot of times that is the first term, but it doesn't have to be. So you have to find the highest power of x, and the coefficient on that term is your leading coefficient. The leading term is the entire term of highest degree. So that variable and coefficient together. So you're going to hear me use all of these terms throughout the next few sections. Mainly degree and leading coefficient will be the big ones that we're going to identify on every problem. The thing about polynomials, so when we graph them, the graph is always smooth and continuous. So you have curves, there's no sharp corners, there's no breaks in the graph, no zigzags or anything like that. Any transformations that we have had before are still going to be true. The other thing, when you're looking at the equation, all the exponents will be whole numbers. So like 0, 1, 2, so forth. You won't see any negative or fraction exponents. That means that you can't have a variable in the denominator of a fraction because that's equivalent to having a negative exponent. So why don't you guys take a few minutes. Oh, hold on. I've got to slide ahead of myself. Let's do this one first. Then I'll have you try the next one. So I'm going to decide if each of these is a polynomial. Is the first one? Yes, it doesn't have any fractions with a variable on the bottom, no negative for fraction exponents, so it's all good. What is the degree for the highest power of x? It's not the first term, but we do see that. Is b a polynomial? A square root, if I wrote it without the radical, is what power? But I said that in a polynomial, the exponents are whole numbers. 0, 1, 2, 3. So this one is a no. There's a fraction in the exponent. Is C a polynomial? No. Why? Is D a polynomial? It is. But the degree is tricky. So I think we talked about this one in the last section. This is what's called the zero polynomial. Remember, 0 is the same as 0x, is the same as 0x squared, is the same as 0x to the 100. Can you tell me what the degree is then? So for the zero polynomial, we actually say it has no degree, because you could put any exponent there and it would be equivalent. Now e, is this one a polynomial? It is. It's equal to just a constant, so we didn't break any of the rules. I don't have a variable with a negative power or a fraction power, so it's okay. The degree. 8 is the same as 8 times x to what power? Because anything to the 0 power becomes 1. So this is like degree 0. Another way to think about degree is like saying how many variables are there. So if you just have a plain 8, there are no variables with it. So the degree is 0. All right, f. It's in factored form. But if I multiplied this all out, would I get a polynomial? Yes. So this one is a polynomial. So the degree. The degree is the highest power of x when it's in this standard form of a term plus a term plus a term. So we don't really have to multiply the whole thing out. We just need to think, okay, if I multiply it, I have 3 x's here. Inside my parentheses, I'm going to get an x squared. When I multiply those together, we get x to what power? Because we would add those 3 x's here and 2 here. So the degree is 5. So you don't have to multiply everything out. Just think about if we did, what would our highest powers be? Any questions on that one? Okay. So I want you guys to take a minute and draw a rough sketch for each of these graphs. You can use graphing calculator if you need to. Just want an idea of what each of those things looks like. X cubed, we've seen that one before. It's our parent function. We've seen, so we know it looks like this. So what's x to the 5th looks like? The same thing. What's the only difference? Yeah, it basically is, you would see it more if you did the 2. On this one you would get 2, 8. On this one you get 2, 32. So it's basically going to get skinnier. It's increasing faster. I don't know that I did a great job illustrating that on these graphs, but so x cubed is going to be a little bit fatter. X to the 5th is going to get a little bit skinnier. All right, x to the 4th, what did it look like? A parabola. Only difference? Your standard x squared is a little bit wider, so this one's just a touch skinnier. What about x to the 6? It's increasing even faster, isn't it? We could see that also if we looked like on the calculator, you can graph multiple things together. Maybe. So if I graphed x squared is going to be my blue one, x to the 4th is going to be my red, x to the 6th is going to be black. So then if I look at these, there's the first, the second, and the third. So you can see it's getting gradually more skinny as it goes on. Okay, but we're seeing everything with an even power looks like x squared. Everything with an odd power looks like x cubed. So we do have that pattern. So it's going to resemble x squared if the power is even, and x cubed if the power is odd. As that exponent gets larger, the graph will narrow. It's just going to get skinnier and skinnier the higher the exponent. But this leads us into a very important concept as we get ready to graph polynomials. We can identify the end behavior of a graph based solely on that degree. So end behavior is what's happening when you have really big or really small x's. So as x is going to positive or negative infinity, which direction are the ends pointing? It is determined by the leading term. So every other term changes the middle of the graph, but the leading term dictates the ends. If it has even degree, we know it's going to look like what? A parabola. So as long as the coefficients are positive, you have your basic parabola where both ends are pointing up. If that leading coefficient is negative, what happens if you have a negative in front? Well, we're still even degrees, so like a negative x squared. They both point down. So if it's an even degree, it's like a parabola, so both ends are going the same direction. Positive coefficient, they're both going up. Negative coefficient, they're going down. Just as an FYI, for end behavior, I'm just going to have you draw arrows, but if you're looking in your book, they say as x approaches infinity, f of x approaches infinity, and as x goes to negative infinity, f of x approaches positive infinity. It's a very long way of saying, but essentially the same thing. If you put in a really big x, you're getting out a really big y. If you put in a really small x, you're getting out a really small y. So just another notation that you might see, especially if you're checking your answer in the back of the book or something. But we're just going to rely on drawing arrows for the end behavior. Okay, if it has odd degree, then we know it's going to look like what? So as long as we have a positive, it's like an x cubed and x to the 5th, my ends are going opposite direction. It's like our normal chair function, so as we go to the negative direction, we're getting out a negative. As we go in the positive direction, we're getting out positive. But what if I give you a negative x cubed? What happens? It flips, so both of those flip. So your end behavior would become up, down. Question set? So let's practice. I want to find the end behavior for each of these. So we look at just the leading term. So that's this. My degree is even or odd? Odd, so that tells me it's going to look like a normal cube. Positive coefficient, so does it flip? No, so my end behavior is just down. Alright, second one. So my leading term is negative x to the 6. So even power tells me it's like a parabola, both ends are doing the same thing. The negative tells me both ends are pointing down, so it's down, down. Alright, these are a little harder because they're in factored form. But we have to think, if I multiply this out, what would be my leading term? So you have that 3 and x. This parenthesis, we would end up with an x squared, right? So when we multiply it all together, we would have a 3x to the third. So what's the end behavior? Down, up. It's like our normal cubic function. Alright, this one, let's see what happens. So we have the 1/2. This one we get an x squared. And this one we have an x squared cubed. So that would give us x to the 6th. And then this one we would end up with an x to the 4th. So when we put it all together, we get 1/2 x to the 12th. So what's my end behavior? Even power, so it's like parabola, positive coefficient, so both ends going. Any questions there? Let's try to create a polynomial for each of these situations. So we kind of had some of these on our homework last night, so we've seen them before. Degree of 3 tells me 3 zeros, and I gave you all 3 zeros. If negative 3 is a 0, what does my polynomial have to have in it? If 2 is a 0, and if 5 is a 0. I told you it had to be degree 4. If 0 is a 0, what do I put? X plus 0, x minus 0, or even x. They're all going to be the same. If 4 is a 0, we put, and if 12 is a 0, x minus 12. What's the degree of this currently? And I need 4. So I didn't tell you which one had a multiplicity. We're just going to have to add it somewhere. But we need one more, and I can't give a new 0, so we just need a square on something. So then it would be 2, 3, 4 for our degree. Last one. Degree of 3. Did I give you all 3 zeros? Yes, so we're not adding any other exponents. If negative 1 is a 0, we write if 1 is a 0, and if 2 is a 0, then I gave you the y-intercept. What is that telling me? Yes, the constant when it's all multiplied out. So we could either multiply it all out and then figure what do we need to make the constant equal 1. Or we could realize this is also like an ordered pair. What's your x value? 0. So it's saying when x is 0, this whole thing has to equal 1. I can't have any more parentheses, but what I could have is a number in front. So let's find that number. So if I put in a 0, equal 1. So A is 1 half. So that means my polynomial is 1 half times x plus 1, x minus 1, x minus 2. Any questions, sir? Just a couple more pieces we're talking about today. Zeros. So we can say the same thing a lot of different ways. If I say a number is a zero, we've been seeing that on those polynomials where you're factoring. We're finding the zeros, basically finding what makes it equal 0. So we could say x equals c is the solution and p of x equals 0. When we plug in c, it makes it 0. A factor is when you have the x with it. So I could say x minus c is a factor. Or we could say it's an x-intercept. So a 0 is the same thing as an x-intercept. It's the value that makes the equation equal to 0. When I ask for a factor, that's when you use the x with it. So take a second on each of these. See if you can tell me all the zeros and multiplicities. What are my zeros? And if it's just a multiplicity of 1, you can write it, but you could also just leave it. Anytime we don't write multiplicity, we're going to assume it's 1. All right, what else? And?
1 half multiplicity of 4.
Okay, and this 5 out here doesn't have an x, so it doesn't change anything. What about b?
0. Minus 1. 2/3 multiplicity of 3. 5 multiplicity of 5.
All right. So the multiplicity of a 0 is actually going to have a big impact on our graph. We're already kind of learning. We know what the ends are going to look like just based off that leading coefficient. We know that the zeros are where you hit the x-axis. Okay. So we know sometimes when you're looking at a graph, like think about a parabola. Sometimes it hits and it bounces off. And other times it might hit at a point and just keep going through. That has to do with the multiplicity of the 0. So if you have an odd 0, the graph goes through that number. So we have some x-intercept c. It's a 0, so we know it's an x-intercept. Our graph's going to hit it and just keep going through. Okay, for any odd multiplicity. If it is an even multiplicity, and we know multiplicities are always positive numbers, the graph will bounce at that number. So we'll have a graph that hits it and bounces off. So that's the even or odd multiplicity. Final thing that we're going to touch on today, and then I'm done. Turning points are where your graph changes direction. So it's like where you switch from increasing to decreasing. If I look at this one, we have a turning point here. So I was going up and I started going down. I have a turning point here, here, and here. Okay, so this graph had 4 turning points. Can you tell me, was this an even or odd degree? I mean, the number of turning points is even. What about the end behavior? What does that tell me? Yeah, even the end behavior, they're both going the same direction. Odd, they're going opposite directions. So the number of turning points is not the same thing as the degree, but it is always at most 1 less. So the number of turning points will be at most 1 less than the degree. So if my polynomial was degree 7, that means I could have 6 or fewer turning points. If it's degree 12, I could have 11 or less turning points on my graph. So if I'm looking at this one, we had 4 turning points. So what would my degree have to be? At least 5. The degree is at least 1 bigger than the number of turning points. All right. And that's really where I want to stop for today. So there's a handout posted on Google